Okay, so welcome everybody. So this is our journal club meeting on February 17, 2021, and I'm happy to welcome Abhinav Deshpande from University of Maryland. So Abhinav is completing his PhD in a few months, and then joining John Preskill by September at Caltech, and he has worked on many things and one of the topics which I found interesting is this complexity phase diagrams. So today he will present about his research here. uh, Abhinav, the stage is yours, please. Yeah.
Thanks so much, Kishore, for inviting me and for that nice introduction. Hi, everyone, and thanks for coming. So today I'm going to be speaking about complexity phase diagrams, and yeah, so we can jump right in. But before that, I'd just like to say, yeah, feel free to ask me questions during the talk because that makes it more interactive. Um, okay, so let me begin by saying that a lot of what we do in quantum physics and quantum computing both is interesting precisely because of this possibility that there's something outside of classical physics or classical computation that we can see. And so this means that it would be nice to identify uh, the so-called quantum signal, which is like a feature that makes a system non-classical. And one way of quantifying non-classicality is therefore to ask this question: when is a quantum system efficiently simulable on a classical computer? Okay, so this is a question that's in the domain of computational complexity theory, where we draw phase like complexity diagrams like this and characterize problems into various classes. So in terms of complexity classes, we are essentially asking what's inside this class BQP. That's the set of problems solvable efficiently on a quantum computer, but outside of BPP, which is the set of problems that you can efficiently solve with a classical computer. Okay, and this is a question that I argue is both experimentally and theoretically interesting. So experimentally, uh, understanding when an experiment can be efficiently simulated and when it cannot can help you narrow down the parameter space where the experiment would yield a quantum speedup over classical computation. Okay. And so in this talk, I would like to mainly argue that this is theoretically interesting as well. And why would that be? That's because complexity theory is inherently a classification tool uh, that helps you classify problems into easy or hard for various classes. And this notion of classification is, uh, yeah, it's a potentially different way of characterizing non-classicality than, say, entanglement. And we have all seen how entanglement has been super successful at classifying phases of matter in physics, uh, such as whether a system is gapped or gapless, whether time evolution of a system has algoricity or not, and whether some interesting ground state is topological or topologically trivial. All these questions can sort of be diagnosed by the entanglement. Okay, so here's where we stand. So on the one hand, we have condensed matter physics where we like to draw phase diagrams such as this, and most questions involve classification. And on the other hand, we have complexity theory, which gives us a tool for classification. So you might naturally ask whether it's possible to put the two together and draw, say, phase diagrams like this. Um, so this is just a cartoon for now, but imagine some, say, disordered quantum system such that beyond a critical disorder, when the system is localized, time evolution is always easy to simulate, even for really long times. Um, you might imagine here that below this critical disorder, the system, say, transitions from being easy to simulate at short times to being hard to simulate at later times. Okay, so that's one kind of phase diagram you can draw. Um, if you consider, say, simulating equilibrium physics, where there's a temperature and a coupling strength, um, you can sometimes get a third phase where your problem can also be quantumly hard. Okay, so we'd like to draw a phase diagram such as this for some hopefully interesting Hamiltonian. But before I get into that, I should first elaborate on what it means to simulate a system. And
Abhinav,
it,
like just small
yes,
question. So, like, can one have like similarly like you have a disorder here, but like recently people are trying to simulate quantum circuits on classical devices with like different amount of noise and all. So like
correct.
does it make sense to have similarly like instead of disorder you have noise,
Yes,
and
totally,
then
totally.
like classically hard versus like classically easy.
Mm-hmm, mm-hmm.
Uh,
Yeah, yeah. With noise, yeah. Like another interesting thing is that there's already a notion of a threshold, right?
mhm,
So below the threshold, um, yeah, you can get arbitrarily close to like an intended uh, quantum circuit or an
mhm,
intended quantum distribution that you aim to simulate from.
mm. Also,
Um,
oh,
right.
sorry, yeah, yeah, please. Mhm.
Good. Good.
Uh, so also I was wondering about this phase thing. So like normally when we talk about phase, like let's say like classical statistical mechanics, we say that it's regions of analyticity of the free energy, and
Right.
then basically at the boundary basically analyticity breaks down
Uh
at the
huh.
phase
Yes.
boundary, and you have different regions of analyticity and so on. So here like obviously you like you will have like different kind of like is there some notion of analyticity here like which breaks at the phase boundary like
There is one sense in which there's a similarity in that there's this argument that the free energy, which is like a sum over uh, exponentials, it's an analytic function
mhm,
for a finite system, right? So the non-analyticity only comes about in the thermodynamic limit
correct
when
correct
you take
correct
the limit. Um,
mhm.
so we'll see a similar feature that for finite systems, you don't really see any transition. The transition is only there if you ask about some inherently asymptotic uh,
Okay,
quantity.
okay. So you have again some kind of like analyticity breakdown for the asymptotic case.
In some sense, yeah.
Okay, thanks. Mhm,
Hmm. Okay. Um, yeah. So as I was saying, there's many ways of defining what it means to simulate physics. Um, Two that are particularly common is so one is that of simulating dynamics, in which we imagine that we can prepare some initial state, evolve it in time, and measure it in a certain basis. The other is equilibrium, where we can say mimic certain equilibrium properties of some target state or target distribution. And for example, both these figures are from the same review paper. So yeah, let me start with dynamics first. I'll So that brings me to the outline. So I'll be first speaking about an example involving interacting bosons, and then talk about localization in the sense of both Anderson and many-body localization. And then we'll talk about equilibrium later. Um, yeah. So I'd first like to define what it means to simulate dynamics. And let's consider the English sense of simulating. Um, the sense is that uh, so there's a classical computer and a quantum computer, and we have a referee who only has access to, say, a transcript uh, written on a sheet of paper by both the computers, and they're asked to distinguish between the two. And um, intuitively, the classical computer is successful at simulating the quantum computer if the referee cannot tell which transcript came from which side. Okay, and here's a bird's eye view of what an experimentalist does. Um, so they take as input some description of an initial state, a Hamiltonian that describes the system, and say some final evolution time. And so the same input is given to the classical computer as well. And now it turns out that many modern quantum experiments are really at their heart sampling from some underlying probability distribution. So for example, if the state produced at the end of the evolution by the experimentalist is this uniform superposition over 2-bit strings, then they're actually sampling from this probability distribution uh, over these 2-bit strings. So what we ask is that the classical computer sample from a distribution DO that's, say, only slightly off. So we want samples from DO from the classical computer. And so we define this more precisely as follows. So imagine that this is the space of all possible probability distributions over, say, n-bit strings. And our ideal distribution is given by, say, a point in the space. And we say that the classical computer should output something that's anywhere within this small ball of radius epsilon around this target distribution du. And we measure this error in terms of the total variation distance between distributions. Okay, so we say that this task of approximately sampling from du is easy if there's some classical algorithm such that two of these properties hold. One is that the runtime of the classical algorithm is polynomial in n, which is like the number of qubits or particles the Hamiltonian is described on. And second, the variation distance between the sample distribution and the target distribution is inverse polynomially small in n. Okay. And we say that the task is hard if it's not easy. Any questions here?
Are there any questions? I mean, I don't see any. I mean, there is something in the
Yep.
chat. Like
Oh, I see. I haven't been seeing the chat.
it says, I thought the non-analyticity comes in moments of the free energy. Mirko is asking something like
Ah,
at a specific heat. Yeah, I think it's the derivative of the free energy, right? Yeah,
mm-hmm,
yeah,
mm-hmm.
yeah, that's from before. Yeah.
Yeah,
Okay. So there is no question from this part.
sure, sure. Point
Okay. Yeah.
taken.
I mean, it's clear. I mean, at least to me, like so far.
Okay. Yeah.
Thanks.
So we now come to this notion of a dynamical phase transition. So let's say we start off with an initial state that was in the all zero state. And the probability distribution looks like this for 2 bits. And mm, that's obviously something that's easy to sample from. Um, Now let's say that after some time evolution, uh, the system becomes, so e to the minus iht times this initial state. So the probability distribution, let's say, looks a bit more complicated like this. And in particular, that it is hard if uh, in the asymptotic case. And now notice that our definitions of easiness and hardness were mutually exclusive. So you can, for every function time t of n, you can ask this question, is simulating the system for time t either easy or hard? and there's like a definite answer for that. Okay. So pictorially, if uh, this is the set of easy to sample from states, and we start off somewhere here, you can imagine that time evolution takes you outside of this set at some point in time. And we are interested in this earliest possible time, t star, at which this happens, at which you go from easy to hard.
So like Abhinav, I mean
Yes.
basically, so let's say that like the Hamiltonian that we are considering is an ergodic one.
Hmm.
So so in that, I mean, what you really mean by this time is that it explores like more part of the Hilbert space or something, and
Yes.
then like at the level of representation, it becomes like a resource heavy to like even represent the uh,
Hmm.
system at the later times or something. So let's say there could be systems which have like a lot of symmetry and all, and they are
Yeah.
constrained, and then even if the time passes, like periodic Hamiltonians or something, where like it always remains easy or something.
Yes. Yes. There are definitely Hamiltonians such that they say only explore like this easy region. Um, and so that's why this whole discussion is interesting if you say restrict the class of Hamiltonians and and study how this timescale T star varies with uh, the class of Hamiltonians you are considering.
So I mean,
Um,
Mirko is saying that he thinks that at the phase boundary you break ergodicity. Is that a right intuition?
uh, so do you mean that beyond this timescale T star you're kind of converged to
No, hi,
something?
sorry. Hi. Now, what I mean
Hi.
is that at least in classical phase transition, so when you have you have different phases, you're breaking ergodicity because you cannot explore anymore um, the entire phase space
Right.
unless you go through you basically you have to have a hard you have to go through a wall, right? So I
Mm-hmm,
think it's
mm-hmm.
the same. In the quantum case, right? Not completely sure about it, but it's yeah.
That makes sense if I look at this picture where I'm drawing a phase diagram where one axis is time and the other axis is something else, and yeah, the other axis is what determines whether you are ergodic or not. I suppose, right? That's the picture you have in mind.
Yeah, yeah, but that's usually for a equilibrium phase transition for dynamical. Yeah. Anyway, thanks.
Mm,
I think it's
yeah,
yeah, it's a little bit more tricky.
yeah, I
Yes.
agree. Hmm, hmm. Yeah, so yeah, we are asking. So as I said, like it makes sense to uh, look at this time scale T star of n for various Hamiltonians or various classes of Hamiltonians and see how it depends on the class. Say, for example, you might expect that, say, uh, chaotic or like fast scrambling Hamiltonians might have a smaller time scale T star than, say, an integrable Hamiltonian. Um, so that's the kind of physics we are after. And so this is exactly what we are calling a dynamical phase transition because it happens as a function of time, and we call it a phase transition because of this fact that at every t of n it's either easy or hard. Okay, so if this was too abstract, we'll now come to the precise example. Um, so hopefully that might clear up things further.
So, sorry, can I ask you something?
Yes.
Maybe I missed this. How do you define in this? So in this case, the hardness comes from the this example you gave that you have. I mean, the easy one is where this everything is picked on one state, and then of course as now you have multiple choices, and so the hardness comes from these multiple solutions, right? The
Um,
accessibility is what is the complexity here? Like in some cases in classical in
Right.
classical mechanics and disordered systems like spin glasses, we define complexity as some sort of entropy. It's very similar
Um,
definition, right? So it's like number of states. So
so
as you go to the, is it? It looks something similar, right?
here,
Is it?
um, it here I would say we don't have a precise number that characterizes complexity, and that's because yeah, this is our definition of complexity in some sense. So we say it's easy if there's some classical algorithm, right? Um,
Okay.
Now, it's hard to show that something is hard because you may not have considered all possible algorithms, and hence you may be thinking that it's hard, but maybe in reality there's some clever algorithm that you didn't think of. Um,
Hmm. Okay.
so that's why here, like in practice, we take hard to be, whatever we can say complexity theoretically by making all these conjectures in complexity theory, um, such as the non-collapse of the polynomial hierarchy, and other sort of less standard conjectures in this field.
Okay. Thank you.
Yeah. Hmm. Okay. So now that that's clear, hopefully, let me get to the example. Um, so we consider a system of bosons hopping on a lattice. So there's a hopping term from, say, site j to site I with this hopping strength jij, and this can be time dependent in general. And there's also a sort of Hubbard repulsion term whenever two or more bosons are on the same site. Okay, so we say there are n bosons and m sites where m scales as n to the beta. And we say, okay, let's say this is on a d-dimensional system, d-dimensional lattice. Further, we start off in an initial state such that these bosons are sort of well separated throughout the lattice. So, so that's because m scales as n to the beta with beta larger than 1. Um, so yeah, so there's so the density of this of the bosons sort of vanishes inverse polynomially with n. Right. So in this setting, when you have this sort of equally distributed initial bosons, the minimum interparticle separation between them scales as follows: scales as n to the beta minus 1 over d. Okay, and this is like an important length scale in our problem. Further, we say that we allow for long range hops, meaning that for a boson to hop from one site to another site in, say, like a one step, it's possible to do that, but the strength of the hopping term decays as a power law of the distance between the two sites. And this exponent alpha in the power law is another important quantity in the problem. And so when alpha goes to infinity, this just corresponds to nearest neighbor hops from one side to another. And when alpha is 0, this just means all-to-all hopping, and there's no semblance of distance anymore. Yeah, the intermediate regime, when alpha is finite, and this on-site interaction string goes to infinity, actually corresponds to that of long-range interacting spin systems. So to summarize, this Hamiltonian models several experiments. So ultra-cold atoms hopping on an optical lattice, and Rydberg atoms with van der Waals or dipole-dipole interactions, and ion traps. So they're all modeled by this kind of Hamiltonian. So let me state our results now. So as a reminder, so we set these parameters: beta equals 2 and d equals 2, so 2 dimensions. So beta equals 2 just means that the number of sites scales as n squared, where n is the number of bosons. And for 2 dimensions, that means that this smallest interparticle separation scales as square root of n. And yeah, so our results are presented in this weird phase diagram. And so on the x-axis here, we have the time represented as how it scales with n. So for example, all constant times appear here, all times scaling as square root of n appear here, and so on. And on the y-axis, we have alpha, which is this power law exponent here. So again, nearest neighbor lies here, and the higher up you go, the more and more non-local your system becomes. So okay, so it's easy to understand this line alpha going to infinity. That's because so what we are saying here is that as long as the time scales smaller than sublinear in this interparticle separation, the problem is always easy. And that's fairly natural because the particles essentially never see each other until this point in time.
Abhinav,
Yeah,
so like this alpha is more like the kind of the interaction strength. Like it tunes the amount of interactions you have between different parts of the system, right? This
in some
it's one
sense,
by
I
Jij.
hesitate to call it interaction because, um, yeah, it's more like a hopping. But
Yeah. So, but what I'm thinking is because of this hopping, like system can get more and more delocalized,
correct,
right?
yes.
And I'm thinking that like we know that if the system is highly entangled, then
Hmm.
it's difficult to like the representation becomes difficult.
Yeah,
So can I like like I can think like try to connect the intuition with the fact that if it's like with respect to time, and if this hopping parameter, if you let the
hmm,
system hop more, and
yeah,
also like for a long time, the
right,
system is getting into like highly entangled regime,
exactly,
and
exactly.
it's becoming a kind of like hard to sample from or something.
Yeah, that's the whole point. Um, yeah. So yeah, for when in the nearest neighbor case, yeah, it's easy to see that as long as this time is sublinear in L, it's easy. And one nice thing is that we can show that it's almost tight. So meaning that as soon as the particles start seeing each other, hardness sets in. And then yeah, one more thing is that just like Kishore mentioned, if you become more and more non-local by going up along this axis, this time scale for until which we know definitely that the system is easy to simulate, and the hardness time scale where we definitely know that beyond this it's hard to simulate. Both of these times decrease, so that gels with this intuition that the more non-local your system is, the faster this hardness sets in. Um, so I should say that there's this intermediate region here where we do not know definitely one way or another whether the system is easy or hard. Um, and that's just a limitation of our proof techniques, because yeah, just by definitions, like the true line separating the two should line somewhere here. Hmm. Yeah, any more questions about the result here?
I have like technique with respect to the proof tech. Like are you going to present the proof technique?
No, sorry, but
Okay,
yeah, I
so
can talk about it.
so
Yeah.
like I'm thinking about the so let's I probably have talked to you like once about this idea. So like so let's say that like I do not, let's say I take some Hamiltonian, which is like poly Hamiltonian, like only poly terms and all. I'm taking
Okay.
it for a reason that like here entanglement, or like let's say the amount of the hopping strength is like the parameter. But
Yeah.
I'm thinking from the perspective of some other quantum feature called contextuality.
Ah. Mm-hmm.
I tune the amount of contextuality on one of the axes.
Okay.
And then like I want to see that like as a system becomes more and more contextual, like
Mm-hmm.
the Hamiltonian, and I have like some evolution time, like do I see some kind of like or like I could have some kind of 3D phase diagram where like could have something like I don't know.
Right.
I mean I can play a bit more. So I'm just thinking like your proof techniques, like how much like they can be translated from one case to another. Like I mean here you tried for this Harvard kind of scenario, but let's say take some spin system like.
Ah. Yeah. So for spins, you can just essentially do the same. You just mentally replace L by sort of just a constant. Um, but yeah, this yeah, I really like this idea about contextuality. Because that's also another way of characterizing non-classicality, right?
Yeah, I
Um,
mean, given the fact that like people have used like entanglement and other things, and for Hamiltonians, like a contextual Hamiltonian and all, only recently it was defined. So it
I
could be
see.
possible that we have like contextuality leading to phase diagrams and all,
Ah,
which
hmm.
hasn't been explored yet.
Yeah, nice. Yeah, but what about the proof techniques? So for the easiness, what we show is that um, we essentially use this idea of Lieb-Robinson bounds,
Ah,
which say that yeah, if you have Hamiltonian evolution for some time t, there's an effective light cone beyond which the
speed limit.
reach of the particle is sort of decaying. And for hardness, we use the time dependence to implement some circuit that's already known to be hard to simulate from other papers, for example.
Mhm.
Yeah. Okay. So let me talk about localized systems, so one of our corollaries is that in this bosonic case, so that in the free bosonic case, if your system is Anderson localized, um, T star is infinity, which is another way of saying that the system is easy at all times. Um, and so you might ask, what about many body localization? And uh, so we have some upcoming work for a 1D MBL Hamiltonian on n spins. Now, this is a setting that differs a bit from the previous setting. So one can't quite directly compare the two. But if you still let me compare, what we see is that uh, the system is, yeah, so sampling or simulating the system is in quasi-polynomial time. So we call that quasi-easy. So it's not quite in P, but um, it's likely to be in P if we can improve our algorithms. Uh, as long as this evolution time is any polynomial. So n to the c could be n to the 100 or so, even. And on the other hand, what we show is that as long as the evolution time scales exponentially, so some authors call this sub-exponential. Um, so it could be e to the n to the 0.1. So as long as the evolution time is this, we can recover hardness. And so this is another way of looking at the difference between Anderson localization and many body localization. Because in Anderson localization, it's always easy, but in many body localization, it becomes hard at, say, exponential times. Yeah, and that's what I was saying. So yeah, that brings me to the conclusion of this dynamics part of my talk. So I'll now speak about equilibrium, and specifically I'll be speaking about ground states. But I think the general picture I would like you to keep in mind is that we want to simulate equilibrium physics at some temperature T. And at if the temperature is high enough, this can be easy because the system is usually well described by, say, like a maximally mixed state. The other extreme is that of ground states, which can be sometimes hard to simulate even quantum mechanically. And so we'll focus on this for the rest of my talk. Um, so now there's an entire field of study called Hamiltonian complexity that studies the complexity of ground states. And so one canonical problem in this field is the so-called local Hamiltonian problem, where we have some local Hamiltonian H, and we want to find the ground state energy of this to say inverse polynomial additive error. And Kitaev showed that this problem was QMA hard in general. And what's QMA? It's a quantum generalization of NP. So this means that it's likely intractable even for quantum computers. And one interesting feature is that these hardness results persist even if you make the Hamiltonians somewhat natural, say by imposing constraints such as spatial locality and translation invariance and so on. And so this immediately brings to mind some conundrum, which is that um, how is it, isn't there a contradiction? Like, is nature solving QMA hard problems or something? Because people think sometimes that nature is preparing ground states of these systems. And so you ask what breaks? And one possible answer is that all these hardness results might be missing some structure that's present in, say, physical Hamiltonians or natural Hamiltonians, that's sort of not being accounted for by these hardness results. And so one of these is the spectral gap. And in physics, we know that the spectral gap has lots of nice properties. For example, it guarantees area loss, the existence of efficient tensor network representations, and rigorous algorithms to compute ground state energies. Um, we also know that the performance of the adiabatic algorithm is decided by the minimum spectral gap from the initial to the final Hamiltonians. But in Hamiltonian complexity, on the other hand, I would say that the spectral gap is somewhat less well understood. So all we know is that existing techniques cannot give you QMA hard instances with a constant spectral
Abhinav,
gap.
there is a comment by Mirko. So he's saying that
What about time?
he's saying that
Yeah,
maybe nature has it's about this QMA
right.
hardness and like finding ground state. So his statement is basically that like nature had a lot of time to prepare those ground states, and it could be possible that nature is not performing some efficient computation to like
Right.
reach there.
Yeah, I really love this question, um, because I think it's philosophically, it's like, uh, is our world well explained by assuming that everything is in BQP, or say, is it a different complexity class? Because if you if you say that right now nature can do whatever you can do in BQP plus this pre-computation time, if you account for this time to find the ground state as some sort of giant pre-computation, right? Um, so that's somewhat akin to this complexity class BQP slash Q poly, where you're given some sort of advice. Uh, but yeah, uh, yeah, I think it's a very interesting question about whether our universe is described by BQP or some, say, higher class. Yeah, right. So yeah, as I was saying, we don't know if QMA hardness persists with a constant spectral gap. And perhaps disappointingly, even if you say that the spectral gap is 1 over polynomial, even then we don't know if you get QMA hardness. And our work fits into this by giving some evidence that the spectral gap can make the problem easier. So there's evidence from the complexity theoretic side as opposed to, say, the algorithm side. And okay, so our first main result is the following. So we have this provable setting where the spectral gap affects the complexity. And to do this, we look at the problem of computing the ground state energy of some gapped Hamiltonian to, say, inverse exponential precision. And by this, I mean that you're assured that the spectral gap of the Hamiltonian is at least delta. And the setting of inverse exponential precision is admittedly artificial, and that's what I mean by setting here. Um, so in the case when you don't have any promise on the spectral gap, because you're tasked to find this ground state energy with inverse exponential precision as opposed to inverse polynomial precision, um, you know the task is p-space complete as opposed to QMA complete. So in this context, what we show is that the moment the spectral gap is at least in inverse polynomial. So note that this is still vanishing with the system size. But even when you have such a weak promise on the spectral gap, the complexity of the problem already reduces by a lot. So it goes from p space down all the way to pp. Yeah, so the spectral gap probably makes the problem easier in the setting of inverse exponential precision. And you should take this with some grain of salt because it's merely going from something very, very hard to something very hard. But nevertheless, that does not deter us from saying that it's maybe true in general. Okay. So yeah, I can take questions here.
Yeah, none. Like maybe you can like
Okay.
proceed.
Yeah. So yeah, our second main result concerns another structure you can add on to the problem. And this is motivated by the following. Sometimes in physics, we often look for ways of preparing ground states. And for a lot of cases where we can also compute the ground state energies efficiently, we also can prepare the ground states themselves efficiently. And so we just say that there's this promise that there is some polynomial sized circuit that can prepare the ground state. Okay. It need not be known to us beforehand. All we know is that it exists. And we again look at the same problem of computing the ground state energy of, say, a gapped Hamiltonian to the same amount of precision as before. So inverse exponential precision. And in this case, when the spectral gap is again inverse polynomial, and you have this additional promise that there's this polynomial sized circuit, in this case, the problem remains PP complete. So again, phrased another way, so this promise that the circuit complexity of the ground state was small makes no difference at all if there's already the presence of a spectral gap. And I like this result because it's very suggestive. So in fact, a much stronger statement uh, is this following conjecture that the spectral gap implies that there exists this polynomial size circuit to prepare a low energy state. Um, so if you believe this conjecture, that would explain why this result holds, because um, yeah, because the spectral gap already implies this low circuit complexity statement. So this extra promise makes no difference. Okay, and this conjecture implies that most natural ground states have smallish circuits to prepare them. And I say this because uh, so I'm kind of abusing the ambiguity of what it means to be natural. But um, say I would say most natural Hamiltonians are either gapped or with constant spectral gaps, or say or gapless at a at a critical point where the spectral gap vanishes only inverse polynomially, and so that's also covered by our conjecture. And yeah, so this is good news for algorithms like the VQE, because if there exists some polynomial size circuit, that's like a prerequisite for VQE to work well. And maybe if you search hard enough, you are bound to find it. Okay. Um, so that brings me to the outlook. Um, so we have seen how complexity can be a way of classifying dynamics. And we saw an example for long-range Hamiltonians and Anderson and many-body localized Hamiltonian systems. We also looked at the complexity of equilibrium states and saw that the spectral gap can affect the ground state complexity. And we had this interesting conjecture, which, if true, would explain why the variational quantum eigensolver works well. And yeah, so I guess for the future, I would like to continue to think about both classical and quantum algorithms for simulation, because these are nice counterparts of complexity theoretic results. And yeah, I'd like to see more applications of complexity theory in uh, drawing these phase diagrams and other features that make ground states of certain Hamiltonians tractable. Okay, with that, I'd like to thank you for your attention and to my collaborators on these works.
Abhinav, so basically, I mean, this is nice result, regarding the spectral gap and the difficulty of simulation. So, uh,
Thank you.
it's nice that like you try to like bring the intuition of variational quantum algorithms there and all.
Mm.
So, I'm just thinking, like there's this result in like NIST community, which says that
Yes.
if you take your objective functions as like like local objective function, then there is problem of like trainability, like barren plateau problem.
Right.
So like if you try to train, you will not be able to. So for local cost functions, like you evade the barren plateaus, like for like longer circuits. On the other hand, if objective function is, let's say, like highly non-local, then in that case, like barren plateaus like come even in the shallow circuits and all, shallow depth circuits. Yeah.
Okay.
So I mean, like, are there any results known? Like, I mean, if the Hamiltonian is, let's say, suppose we are trying to find the objective function is, like the expectation value of the Hamiltonian, like the ground
Uh-huh.
state energy you are trying to find. So if
Mm-hmm.
the Hamiltonian is highly non-local, uh, would does it mean that the spectral gap there like vanishes? Like, I mean, so in your case it would be something like, if let's say the alpha, like, I mean, if I kind of tune the alpha is such that the hopping
Right.
strength goes like up, then in that case, like do you have any results, or like are you aware of anything which relates to the spectral gap? Because then one can like relate it with the barren plateau thing, that maybe like in that sense, Barren Plateau is, like, I mean, maybe I talked to you a bit about this, the Barren Plateau. This was
Right.
mentioned by Alexei to me, that could
Yeah.
be Hitler's way to stop from getting to the ground state.
So one question about these, about the result that you mentioned.
Uh,
So you mean local in the sense of spatially local, right? And not
uh,
necessarily in the sense of, like how many particles are interacting under one Hamiltonian term
no,
or
no,
so.
no. What I mean is more like, like it's like number of qubits on which they act. So like it's like let's
Hmm.
say two local or three local, like
Right. Okay.
yeah,
So
yeah,
it's the computer scientist local.
yeah,
Um,
yeah,
uh,
yeah.
uh, yeah, I can see that working out more. Yeah, the reason I asked is because you linked it to this alpha thing, right? But
Yeah,
alpha
there is
was
one
more like a
initial one. Yeah,
that was more like spatial locality.
yeah, yeah,
Um,
yeah.
yeah, intuitively, I do agree with you about how the more non-local Hamiltonian is, perhaps the spectral gap, is smaller. But I have no idea how to prove anything like that.
Mm.
Mm. Hi, I have a question.
Hi.
So thanks for the really nice talk. So
Thank you.
I was wondering if there are any cases where um, after a certain point, if you increase the long range interactions or long range hopping, it can actually make simulation easier. In this, I'm being very like non-rigorous in my thinking. Just based on, this notion that is seen a certain critical regime, and if either on either side of it, usually things are too boring or like
I see.
not just happening.
Hmm. Um, yeah. So at criticality, I would definitely agree that there's very interesting things happening there. Mm, yeah, but that's also just at the cusp of hardness setting in. So it's like, yeah, in this sort of setup that we are dealing with, the further into the further deeper into the hardness phase you go, the harder it becomes in some sense.
Okay.
Mm,
So for example, in your alpha, there is just, you know that it's just a one-way street, right? No matter how small you make alpha, it's only going to get harder.
right. Yeah,
Okay.
because I can simulate a system with large alpha by one with the smaller alpha. So
Oh, okay. I see. So
right.
the another question I had is somewhat related, which is uh, so what if you identify certain observables as these are the things you're interested? Does
Okay.
that significantly change the statements about what is hard and easy, or what
Yeah,
regimes are?
I think it should, because when we ask for samples from the full distribution, we are sort of being maximally charitable to the experiment, and
Okay.
we are being as broad as possible when we say that this is what the quantum device does. Um, but on the other hand, if you're just interested in, say, like a few observables, um, then then it's possible that, say, a classical computer you know uh, might simulate those observables pretty well for you, even though it doesn't know how to sample from the full distribution.
Okay. I wonder if this can be made somewhat into like a recursive kind of definition, where
Huh.
the complexity of the simulation you also sort of base the definition on the complexity of actually being able to tell apart the actual full simulation from something that captures effectively those observables that you can ever
Right. Yeah, I think
Yeah.
actually I have thought along these lines a bit, but um, I don't really have any concrete things there. And the motivation for why I considered this question, at least, was from the point of view of verification, because in these sampling problems, there is not a clear way of telling whether you are in actuality sampling from the target distribution or even something that's inverse polynomial close away, close to it.
I see.
Yeah, but if you sort of, if you changed your notion of distance from, say, total variation distance to something that you can say, like a more operational measure, like the one you mentioned, like whether can you tell the two distributions apart,
Right.
maybe that's a better way of quantifying it. And well, the total variation distance does have a nice operational interpretation.
Mhm.
It is related to the probability with which you can tell the two distributions apart in the limit of, say, a large number of samples.
Right.
So this could be exponentially many samples.
I see.
But if you restrict this to be somewhat more reasonable,
But also, right, it's probably under the assumption that you have access to arbitrary observables or something. Like you can
That's
make
right.
any kinds of measurement.
Yeah, like you are sampling from the distribution, and that's the data you're getting, and
Okay.
then you are inputting the numbers from, say, one box and from the other box into a computer, and there's some test that somehow tells you.
Right. Okay. Thanks.
Sure.
Yeah, thanks, Varun. So, are there any more questions?
Yeah, actually, I would be interested in seeing if this had any nice quantum machine learning connections, because that's not something that I usually think about. And like, I say this because, like, I'm interested in, say, classifying dynamics, and when a machine learning person sees classification, like, I think their eyes immediately light up. So I don't know whether any of you have, say, nice insights on this.
Yeah, at least I cannot see something like on the fly, but like, apart from this Baron plateau stuff, like, which is not really machine learning but comes from the optimization, but maybe kind of related. But yeah, I mean, like, super interesting, like, and very pedagogically, like, you presented without like much jargon and all, like
Good to know.
yeah. So if there are no more questions, then let's thank Abhinav for such a nice talk, and I believe like this will like lead to some discussions and probably some work in future. So thanks a lot, Abhinav. I mean, for this nice
Thank
talk.
you all.